In this video, we're going to talk about systems of linear inequalities, which is where we have multiple inequalities at the same time, and we want to know where all of them are satisfied. And the places where all of them are satisfied is called the feasible set. Okay, so what we're going to do is we're going to look at these systems, but we're going to solve them graphically. Okay, so if you look down at example 1, so we want to graph this system of inequalities, and what we're going to do, because we're solving it graphically, is we're just going to graph each inequality separately on the same grid, and then look for where their solution sides intersect. Okay, now because we were shading the side that didn't have the solutions, it's going to be clear where they overlap, so we don't have to do much work there. So the set of points x, y that simultaneously satisfy all the inequalities, this is called the feasible set. Okay, you might also see it as the solution region or the feasible region. So this is what we're looking for. Just a note here, from now on, we're only going to be considering inequalities where equality is included. Okay, so we don't ever have to worry about dotted lines. We're going to always have filled in lines now, because we always have equality included. So when we look at this example, I want to graph the first inequality and then the second inequality, and I'm going to do these in different colors. So if we look at number 1, we want to graph this equation with equality. So x minus y equals 5. So you could, if you wanted, change this into slope-intercept form. So I'd want to add y to both sides, so that goes away, and then subtract 5 on both sides so that the 5 goes away, and then it will simplify to y equals x minus 5. So we're going to have a y-intercept at -5 and a slope of positive 1. Okay, so we could go ahead and graph that on our grid. So 1, 2, 3, 4, 5. So that's at -5, 0. I lied. 0, -5. Okay, and then the slope is 1, so we go up 1 over 1, up 1 over 1. Okay, so our line is going to look like this. Okay, we want to get in the habit of labeling our line, so this is the line x minus y equals 5. Okay, so we graphed our line. Now what we want to do is our test point. So again, you can pick any point you want as long as it's not on the line. I like to pick 0, 0 when it's not on the line, so that's what I'm going to do. So let's test 0, 0, and I'm going to plug it into the inequality. Okay, so 0 minus 0 less than or equal to 5. So that says 0 is less than or equal to 5. Okay, this is true. So 0, 0 is on the solution side. So what we're going to do is shade the opposite side. So the side that does not have 0, 0. Okay, so all of those are out. Because they're not solutions to the first inequality, they're definitely not going to be in our feasible set. Okay, now we want to do the same idea, but for the other line. Okay, so now let's do number 2 here. Okay, so we want to graph 4x plus 2y equals to 8. Again, you could put it in slope-intercept form. I'm just going to find 2 points. So when x is 0, 2y has to be 8, which means that y is 4. So I get a point at 0, 4. Okay, when y equals 0, I'm going to have 4x is equal to 8, which means that x has to be 2. So I get a point at 2, 0. Okay, and I want to graph the line. So I just need to connect those points. Okay, remember to label your line. So this is 4x plus 2y equals 8. Okay, now I want to do my test point. Okay, so again, I'm going to pick 0, 0, plug it into the inequality. So 4 times 0 plus 2 times 0 bigger than or equal to 8. So that's 0 plus 0 bigger than or equal to 8. So 0 is not bigger than or equal to 8. Okay, so this is false. So that means I want to shade everything that's on the same side as 0, 0. So now all of these are gone. Okay, so this part here, these points in this region, they don't satisfy either of the inequalities. Okay, these points are out because they don't satisfy the green number 2 inequality. Okay, these points are out because they don't satisfy number 1 inequality, even though they do satisfy number 2 inequality. So our feasible set, oops, I spelled it wrong, is going to be the part that's left unshaded. Okay, so it's going to come down the green line to this point here, and then up this blue line. So everything in this region, okay, in this little triangle shaped region that goes on forever, all those points are in the feasible set because they're going to satisfy both the inequalities simultaneously. Okay, maybe we want to check. So if I take 3, 4, okay, it looks like that this will be in my feasible set. So let's check that point. Okay, you don't have to do this normally. So 3 minus 4 should be less than or equal to 5. So that's -1 less than or equal to 5. Okay, that's true. Now when I do 4 times 3 plus 2 times 4, I should be bigger than or equal to 8. So that's 12 plus 8, bigger than or equal to 8. Yes, that's definitely true. So you see the point here, which I picked sort of at random in this area I call the feasible set, satisfies both inequality 1 and inequality 2 simultaneously. Now, this point here is kind of special, so we call it a vertex or a corner point of the feasible set. Okay, so this is a corner point. Because it's it's the intersection of two boundary lines. Okay, so this one happens to be the only corner point, but there could be multiple. So it is useful to actually find these corner points. So maybe let's just try and find that here. Okay, so let's call this point P. So to find P, it's the solution of x minus y equals 5 and 4x plus 2y equals 8. So we can use what we did in section 4.3. So I want to take one of these, okay, maybe the first one, and I say, okay, x has to be y plus 5. Okay, then I'm going to take that and plug it into x in the other equation. So I'm going to have 4 times y plus 5 plus 2y equals to 8. So 4y plus 20 plus 2y should equal 8. So I have 6y equals -12. So that tells me that y should be -2. And then I can take this and plug it into here to tell me that x should be -2 plus 5, which means that x is 3. So our coordinates for P are going to be 3, -2. And it looks like that P is actually at that point, 3, -2. So our drawing's pretty good as well, which is nice. Okay, let's try another one. So let's solve this system of inequalities graphically, and we want to find all the vertices or corner points here. So let's call this 1. So I'm going to start, actually I'm going to start with these ones. Okay, this is 3 and 4, because they're actually the easiest ones to do. So x equals 0. This is the y-axis. Okay, so I start with that. X equals 0. Now, I don't even really have to test a point here, although you can if you want. So I'll be using pink. So if I want to be bigger than 0, it means that I need x to be positive. So x should be to the right of this line. So that means everything to the left is out. Okay, similarly, y equals 0 is the x-axis. Okay, now if I want y to be bigger than or equal to 0, it means I want to be above this line. So everything below this line is out as well. Okay, so those ones are done. Okay, now number 1, we have x plus 4y equals to 12. Okay, so I'm going to find 2 points. So when x is 0, 4y is equal to 12, which means that y should be 3. So I get a point at 0, 3. And when y equals to 0, I immediately get x equals 12. So I get a point at 12, 0. And this is 0, 3. Okay, so I connect those with a line. Okay, remembering that I should label it. So this is x plus 4y equals to 12. And then I want to test a point. So again, I'm going to test 0, 0. So 0 plus 4 times 0 is less than or equal to 12. Okay, that's true. So 0, 0 is on the right side. So that means I want to shade, I'm going to do it in yellow, everything that's above this line. So all of this is gone now. Okay. So now I want to do number 2, the last one. Okay, so I have 2x minus y equals to 6. So x equals 0 means minus y is 6, which means that y is minus 6. Okay, that's not really on my grid, so maybe I want to find a new point. It's still a point, okay, but it just doesn't really, it's not nice to graph it here. So if y is 0, I get x, so 2x equals 6, which means that x is 3. 1, 2, 3. Okay, and maybe I'll try x equals, I don't know, 5. So that means 2 times 5 minus y equals 6. So 10 minus y equals 6. So that means y is equal to 4. Okay, so when x is 5, 1, 2, 3, 4. Okay, so let's draw this line here. Okay, so this is the line 2x minus y equals 6. And we want to test a point. 0, 0 is not on this line, so let's check that. Plug it into the inequality. So 2 times 0 minus 0 should be bigger than or equal to 6. So 0 is bigger than or equal to 6. Okay, that's false. So that means that I want to shade the side that has 0, 0. So all of these are out. So the feasible set is going to be anything that's not shaded. Okay, so that's going to be this little triangle bit here. Okay, so this is the feasible set, and we're going to have 3 vertices. So let's call them A, B, and C. Okay, so remember in this question we wanted to find the vertices, or the corner points. 2 of them we've already plotted, so we actually know 2 of them. Okay, so we have so 3 vertices, or corner points. Okay, so A, we already know, is the point 3, 0, because it was this point here that we found on line 2. Okay, we also know B is the point 12, 0. I want a color I haven't used, so let's use this one. So we found that up here. Okay, it was the x-intercept of the line number 1. Okay, and then point C is going to be the intersection of the blue line and the purple line. Okay, so we need to find C. It's the solution of the system, what is it? X plus 4y equals 12, and 2x minus y equals 6. Okay, so I'm going to use substitution. So let's take this line. It's going to be y is equal to 2x minus 6. Okay, so then I'm going to take that and plug it in for y in the other equation. Okay, so x plus 4 times 2x minus 6 should be equal to 12, which means x plus 8x minus 24 should equal 12. So I want to add 24 to both sides. Combine the like terms, so 9x should be equal to 36, which means that x should be equal to 4 if we divide by 9 on both sides. And now I can take that and plug it into here. So y is 2 times 4 minus 6. So 8 minus 6 is 2. So our point C is going to be the point 4, 2. Now, does that make sense for our graph? 1, 2, 3, 4. Yeah, it looks like it should be at 4, 2. So we found we found the feasible set, and we also found the 3 corner points associated with this. Now, there's a notion for the feasible set or solution region of boundedness versus unboundedness. So we say it's bounded if you can enclose it within a circle. Okay, so we see this feasible set here is contained on all sides. So that means I can put a circle around it. So this one would be a bounded feasible set. Okay, now I think that the one that we did in the first example here, this one would be unbounded because these lines go on forever and there's no boundary over here. So I can't draw a circle around it because it goes forever in the sort of vertical direction. So this one would be an unbounded feasible set. Okay, I think we have just one more example. So we want to solve this system graphically and find all the vertices. So again, I'm going to start with the bottom here. So y equals 0 is the x-axis. Okay, and I want to be bigger than 0. So that means everything below the x-axis is gone. Okay. Make it yellow, I guess. Actually, I want a better yellow. A brighter one. Okay. So this can be number 2. Actually, I don't know if you can see that. Okay, well, let's make it green then. Okay, so number 2 is x equals 3. So that's going to be the vertical line, okay, at x equals 3. And we want to be bigger than or equal to 3. So that means that the parts to the left of this line are gone, because those values are less than or equal to less than 3. Okay, so those are gone. Now, let's do this one in blue. Okay, so line 3, I have x minus 2y equals to 0. So if we try to find the intercepts, Okay, x equals 0 means minus 2y equals 0, which means y equals 0. So here I get a point at the origin. So I can't use the y equals 0 because then I'll just get x equals 0. So let's try maybe x equals 2. Okay, so 2 minus 2y equals 0, which means 2y is equal to 2, or y is equal to 1. So at x equals 2, y equals 1. Okay, so I get a point like that. And my line's going to look something like this. Okay, so this is the line x minus 2y equals to 0. Okay, now I want to test a point. Here, I cannot test 0, 0, because 0, 0 is on the line. So it's usually best if you test something on one of the axes. Okay, it's the clearest to know that it's not on that line. So I'm going to test something up here. So maybe 1, 2, 3, 4, 5. I don't know. Let's say 0, 6 is what I'm going to test. So x is 0, y is 6. So 0 minus 2 times 6 should be bigger than or equal to 0. So that says minus 12 is bigger than or equal to 0. Okay, that's false. So that means that the point that I selected, okay, which was 1, 2, 3, 4, 5. This point here is on the non-solution side. So we're going to shade the side that contains that point. Okay, so all of these are also gone. Okay, one more line. So let's do this fourth one maybe in orange. Okay, so here I have x plus 2y equals to 5. So when y is 0, we get x equals 5, so that's nice. 2, 3, 4, 5. So we get a point down here. 5, 0. Okay, if x is 0, we get 2y is equal to 5, which means y is 5 over 2, which is 2.5. Okay, so that's going to be about there. Oops, I can't turn it that way. So if I connect those, okay, this line is going to look something like this. So this is the line x plus 2y equals 5. So here I can test 0, 0 because it doesn't go through that point. And it's going to be 0 plus 2 times 0 bigger than or equal to 5. Okay, that's 0 is bigger than or equal to 5. That's false. So 0, 0 is on the bad side. So that means everything below this line is gone. So, oops. Our feasible set looks like, now here it's maybe a bit, we might want to be careful here. So I'm going to guess that it has 4 or 3 corner points. Okay, so this set here is our feasible set. So it looks like that we have corner points A, B, and C. But we should check this point here. So, but where the orange and the blue meet, we want to make sure that the x value is less than 3 there. Okay, so let's just check that first before we start computing these others. So here's where, if you have a really accurate graph, you probably know that it's not, but let's just check. So let's call this point D. So D is the intersection of x plus 2y equals 5 and x minus 2y equals 0. Okay, so this means that x is equal to 2y. So if we plug that in here, that means that 2y plus 2y is equal to 5. So 4y is equal to 5, which means y is 5 over 4. And x is 2 times the y value. So that, oops, I already did the multiplication here. So 2 times 5 over 4 is 5 over 2, which is 2.5, okay, less than 3. So this means that this is outside the feasible set. Okay, so that's good. So our corner points now, corner points are going to be A, B, and C. Okay, now C we already know. Okay, it's even marked here already. So that was the x-intercept of the orange point, or the orange line. So that's 5, 0. Now for A and B, they're on the green line. So to be on the green line, they have to have x-coordinate 3. So A is also on the blue line. Okay, and the blue line is x minus 2y equals 0. So to find the y value, let's actually do this in blue. Okay, so x minus 2y should be 0. So x is 3. So 3 minus 2y should be 0, which means 2y equals 3, which means y is 3 over 2. Okay, so our y value here is 3 over 2. And then for B, we're on the orange line. Okay, so that has equation x plus 2y equals 5. So when x is 3, I have 3 plus 2y equals 5. Subtract 3 on both sides. 2y equals 2, which means that y equals 1. So here our y value is 1. So those are our 3 corner points for this system. And notice that it would be unbounded because it's open on this side. So we can't contain it all within a circle. Okay, so this is an unbounded feasible set.